Alrighty, hello everyone and welcome to today's lecture. I'm super glad to have you guys all here. So my name's Alice and I'll be your lecturer for today for the Year 11 Maths Advanced 8 Notes lecture. I'll introduce myself a little bit more in a bit, but just to start, a little bit about 8 Notes. So 8 Notes has just been offering lots of free resources to students to help you do well in your studies, to maximise your marks come exam time as well. So we've been around since 2007 and these free lectures have been running since 2015. And pretty much these free lectures are just about helping students as much as possible. This one in particular for January Maths Advanced is just giving you a little bit of a head start, I guess, on maths for the year to come. So a little bit more about the free resources with 8 Notes. So first of all, there's lots of study notes available on the website, covering a broad range of subjects, so not just maths. You'll be able to go on the website, look up your subject and see if there's any notes available for you. There are some usually notes available for most subjects. Then you've got lectures given by past students who have done well in the subject. They're giving you their personal experiences and telling you how to do the very best in your exams. Different discussions that become super important, and you'll probably look at a lot of them once you get into year 12 at the end of the year. And then some videos online just to give you some revision in, I guess, a bit of a different format. Newsletters, the ATAR calculator, which for you guys in year 11 isn't probably something that you've looked at yet, but everybody gets to that point in year 12 where you start looking at the ATAR calculator, working out what marks you need to get the goal ATAR, and pretty much if you're anything like me, you're using that ATAR calculator to work out how low can your marks go while still getting your goal ATAR. And there's also different articles and lots more available as well. So then there's also 8 Notes Plus, which is a subscription service. So included in 8 Notes Plus is all of the 8 Notes like study guides, text guides. So those text guides do exist for most year 11 and 12 texts for English. And then, yeah, there's also flashcards available for some subjects, and then your complete course notes, as well as some subjects have topic tests included in like a little book. And then there's also the AI answer bot on there as well. If you're interested in looking at that, you can Google 8 Notes Plus and it should come up. But onto today's lecture. So hopefully you guys are all here for Year 11 Maths Advanced lecture. So this is the January lecture series. It's giving you a bit of a head start going into Year 11. And so I'm glad to have all of you guys here with me. So like I said before, my name's Alice. I am currently studying medicine at the University of Newcastle, and I graduated in 2022 with an ATAR of 99.3. And those are my subjects there. I did only 10 units in year 12. And then in year 11, I actually did 12. I started off with 13, dropped extension English after about 2 weeks. So pretty much did 12 units for year 11. And I actually had a bit of a change with my subjects going from year 11 to year 12. So don't fret. I know for me at the beginning of year 11, it was a bit, scary, thinking like, what if I don't like my subjects? Thinking that I couldn't change them for 2 years. But I will say I did like a fairly big change. So in year 11, I did biochem, economics. I started with extension English, extension maths, and 1 unit religion. And then at the end of year 11, I picked up a 2nd unit of religion. I dropped extension maths and dropped extension English, although I dropped extension English in like week 2 of term 1. So I don't really know if that counts, but yeah, like it is possible to change your subjects around. So if that's something you're worried about, don't stress. And so yeah, those are the marks I got for my subjects in the end of year 12. So yeah, and then I tutor all these subjects at TutorSmart if any of you guys are interested in getting some private tutoring. And I also run the advanced HSC math class if any of you guys are looking at doing that for year 12 next year. So that maths class is for the HSC, so it'll be more relevant to you guys for next year. So yeah, this is my third ATAR Notes lecture series. If you've watched some of these lectures before, which you probably haven't, if you are in year 11, because I've done pretty much year 11 and year 12 lectures, but if you have, you may have seen me in some religion and maths lectures in the past. And yeah, like I said before, I tutor the Advanced Maths HSC class. It's just about creating specific resources for you to help you achieve your goals. There's also other classes available for some of the HSC subjects if you are interested in that next year. And then I also do some private tutoring for HSC prep in these subjects that I was talking about before, if any of you guys are interested and want a little bit more help from me or from one of the other tutors at TutorSmart. So a little bit about what today's lecture is going to look like. So the lecture will go for about 2 or so hours, probably a little bit less than 2. And you can pause it at any time if you want to take a break. When we're going through questions, I probably won't give you too much time to sort of attempt the question yourself. So if you do want to attempt the questions before I go through them, pause the video when we get up to them, have a go, and then you can keep watching it. If you are watching this recording live, you can ask me questions. I'm in the chat. I'll say hello, and I'll be there to answer any questions as you watch the lecture. And then you do have access to these slides as well on the lecture page, so don't worry about copying everything down. Write down the important examples, questions, things like that. And so because this is at the beginning of year 11, some of this stuff is going to be brand new content for you, and you're never going to have seen it before. So it's okay if you're feeling a little lost. I definitely was lost when I first looked at some of this stuff. Particularly when we get down to trig, some of that trig stuff is going to be brand new to you. So yeah, it's okay if you're feeling a little lost, don't stress about it. Just take your time going through the lecture, and remember that you're at the beginning of year 11, so you're going to be doing all of this again in class anyway. And I will say year 11 maths is kind of important. If you guys know me at all, you know I kind of do preach that year 11 isn't that important and that you can sort of change your attitude from year 11 to year 12. The one exception I will say to that is maths, because a lot of your maths concepts from year 11 form the foundations for the stuff you do in year 12. So if you don't know the stuff from year 11, you don't have the basis knowledge to do your year 12 stuff. Particularly looking at calculus, which we won't be looking at in today's video, but when you do get to it in class, your calculus stuff, your function stuff, and your trig stuff, all super important for year 12. Because if you don't know the year 11 stuff, the year 12 stuff is going to be even harder. So yeah, I would say year 11 maths is important, so make sure you're paying attention this year and you get it down as well. But then again, on the same token, if you know year 11 is not your year in the end, don't stress. Nothing from year 11 carries over into year 12, so you can pretty much completely start fresh in year 12. Maybe it'll be a little bit harder, but don't stress yourself out too much about year 11. So with today's lecture, we're going to be looking sort of 4 areas, so 2 topics from the year 11 syllabus, so that being working with functions in trigonometry, and then interspersed between those things, just some study tips and some exam technique stuff looking at maths in particular. This is important, and I would say it's important to pay attention particularly to the study tips and the exam technique, because year 11 and year 12 maths is very different from what you do in junior school. So from year 7 to 10, so your studying is going to look a lot different, and your exam technique is going to look a lot different. One of the big reasons for that is that your exams, depending on your school, but your exams may start being 3 hours this year, or some schools, they'll start being 3 hours next year in year 12. But it's super important to learn different techniques for sitting a 3-hour exam, because it is quite different to sitting a short exam. Not only do you have to focus for the 3 hours, but you have to remember a lot more content. There's a lot more question types and things like that go into a 3-hour exam. So yeah, that's today's lecture. We're going to start with functions, then give yourself a little bit of a brain break with some study tips before moving into trig, and then looking at exam technique to wrap it up as well. Alrighty, let me have a quick drink before we start. And like I said, if you guys are watching this live, feel free to ask questions at any time. Maths related, study related, school in general. If you do have any questions, just check them in the chat and I'll answer them for you as best as I can. So we're going to start today looking at working with functions. So this topic for most schools is the first bit of year 11. Some schools do it in a bit of a different order, but yeah, it is important. You do need your function stuff again in year 12. There's a fair bit to functions, I would say, so we will jump straight into that. So the first thing we're going to look at is what is a function. So when you're talking about functions and when you do this at school, you're going to be introduced to two topics or two concepts. So the first concept is a relation and your second concept is a function. And so one of the key things you need to be able to do is to differentiate between a relation and a function. So a relation is a set of ordered points with coordinates x and y, where your x and y variables are related according to a specific rule. So I've got here the example of x squared plus y squared equals 25. And I'm hoping that you recognize that that is the equation of a circle. And so essentially what that's saying is that whatever coordinates we put into that equation, they are going to fit a certain rule so that your x squared plus your y squared will equal to 25, right? Then we have a function, which is a specific type of relation which for only have one y value for any x value. So essentially what that's saying is that when you have x values on your x-axis, each of those x values is only going to be related to one single y value. So let's think about this in terms of the examples that I've got written down there. So with the example for a relation, if you imagine a circle sitting on your coordinate axis, let's say we've got, a point on your x-axis here. That x point is going to have a y point at the top and the bottom of your circle, right? So with that, each of your x points has two y values. Okay, so they are related. There is a rule that dictates that relation, but each of your x values has two y values, so therefore it is not a function, right? Because the thing that differentiates a function from a relation is that your functions are only going to have one y value for each of your x values. Okay, so then looking at that example, y equals x squared, hopefully you recognize that as the equation of a parabola. If you're thinking about your parabola and you think about that in your head, any parabola can be positive, negative, whatever pleases you. If you pick any x value on that coordinate plane, you're seeing it in your head, you'll recognize that each of those x values is only associated with one y value. And that is what makes that a function, okay? If the x values only have one y value. So another example of that would be a cubic function. Each of those x values only has one y value. Straight lines usually are only are functions unless they are vertical lines. Otherwise they are going to be your y values as well, okay? With a function, it's important to recognize that two x values can be associated with the same y value, okay? So essentially, thinking about that parabola again, parabolas are symmetrical, okay? So let's say if we have the function y equals x squared, you're going to have a value of x equals 1, and at that point, y is also going to equal 1. And then you're going to have when x is equal to -1, y will also be equal to 1. And that is still a function, right? So you can have the same y value for two different x values, so long as no single x value has more than one y coordinate. So yeah, that is how you tell the difference between a relation and a function. We're going to look a little bit further about how we can tell the difference between relations and functions when we're looking at graphs as well. So we do something called the vertical straight line test to test whether something is a function or whether it is a relation. Okay, so something else that comes up, sorry, I just remembered this, sometimes in exams is thinking about all functions are relations, but not all relations are functions. Okay, so if we go back to that slide before, we'll see a function is a specific type of relation. Okay, and the defining feature is that every x only has one y. Okay, so a function is always going to be a relation, but relations are not always functions. Okay, anyway, little side note there, we've got the vertical straight line test, and this is how you can tell whether something is a function or not. So for any graph you've got, this is looking like the graph of sine, and then you've got the graph of a circle over here. So for any graph you've got, if you draw a straight line through the graph at any point, you should only intersect the graph once. Okay, so it's important to recognize that the straight line has to be drawn anywhere. There are some graphs where there'll be points where it only intersects once and other points where it intersects twice. So pretty much if at any point on the graph, if you drew a straight line and you'd intersect the graph twice, it's not a function. Okay, so like this circle here, we've drawn the straight line down this random point here, and we can see that it intersects the graph twice. So essentially what this is representing is that the graph has two y coordinates for this specific x point, because when we draw a straight line, we are essentially drawing this equation, a line with the equation x equals something, okay? And in doing that, drawing a line with x equals something, if it intersects the graph at 2 points, that x has at least two y coordinates. On the converse, if we have a straight line going down our graph and it only intersects once, that means that x equals whatever that line we've made it equal to only intersects the graph once, therefore it only has one y coordinate. And that is how we can tell graphically whether something is a function or not. So you may be asked to do that in an exam to perform the straight line test or to determine whether a graph is a function or not. The other way is once you look at these enough, you will be able to sort of just look at your graphs and pick up whether or not they're going to be functions by just looking, is there any x coordinates that have more than one y coordinate? But that's not something that you need to do right now. That's just as you start to look more and more at functions, you'll be able to start picking up whether something is going to be a function or not. So something important to know, and you will use this from literally the beginning of year 11 to the end of year 12, is about function notation. So you may have been introduced to this in year 10. Some schools do introduce it, some schools don't. It doesn't particularly matter. So if y is independent on the value of x, then we say y is a function of x, which is essentially written as y equals f of x. So this is a little bit tricky to think about. So when we say we have f of x, so just this bit here, this is meaning x being the function, the numerical value or algebraic value that we are substituting in to the function. Okay, so if we've got a function and it's x squared, and we substitute x into that function, we are going to end up with x squared, right? If we have x squared and we have f of 1, we put 1 into that equation, we'll get 1 squared, that's equal to 1. Okay, so we'll have a bit more of a look at an example in a minute, because it's a little bit tricky to get your head around without seeing an example. But essentially what this means is that our y coordinate is equal to f of x. So our y coordinate is equal to substituting x into the function. So since y is equal to f of x, then f of a is the value of y at the point of the function where your x is equal to a. Okay, so whatever is in these brackets when we're looking at a function, that is what you're substituting into the equation in place of whatever pronumeral is in your function. Usually it is x. I mean, sometimes your equations are going to be given to you as like, a or b or c or anything. Usually it's x. They don't try and confuse you that much. But whatever value, so that can be a number, it can be a letter, is in these brackets, that's what we're substituting in place of our unknown in our original function. So we have come across our first example of example question for today. So if f of x is equal to x squared plus 4x plus 4, find f of a and then f of minus 3. So I will give you guys about 30 seconds or so just to have a go at this question. If you need more time, pause the video and then we'll go through it together. Alrighty, so if you need more time, pause the video here because I'm about to do a big reveal of the answers. So looking at the first part, so part A, our original function is fx equals x squared plus 4x plus 4. When you have a function given to you like this, usually it is fx. Essentially what that means is x is kind of just like your placeholder. So it's saying like, we're not substituting anything in there yet, but when we do substitute things in, we're substituting them in place of this x. So that means when we have f of a, we are putting a in wherever x was in our original function. So then we end up with a squared plus 4a plus 4, right? Because all we've done is substitute a in place of x in that original function. So doing it with pronumerals is typically pretty easy because you're essentially just exactly replacing your x's for whatever pronumeral you've been given, okay? Doing it with numbers is a little bit trickier. So we'll have a look at this example for part B. So we've got f of minus 3, and what that is substituting in minus 3 wherever there was an x in our original equation. So what we do is we do minus 3 squared. Please remember when you're doing these questions, if you are being asked to substitute in a negative value, you must put brackets around them. Otherwise, you're going to end up with the wrong answer when you square it, okay? If you don't put brackets around that squared and you chuck it in your calculator here would spit out -9. But that's not the case here because we need to substitute this whole entity, so this whole -3, where the x is, and in this case, the whole x is being squared, so the whole -3 has to be squared, right? So you put it in the brackets, square it, and your calculator will spit out 9 for you. Depending on your school, depending on the markers and stuff you get, some markers will actually mark your working as incorrect if you don't have your brackets around your negatives in this sort of situation. So do keep that in mind. We've got -3 all squared plus 4 -3 plus 4. See, in that first line, all we've done is substitute in -3 wherever there was an x in our original equation. Then when you have actual numerical values, perform the equation. So you can either do some mental maths or pop it in your calculator. I would say it's always good to write out every step of your working, just in case something goes wrong. So then you've got -3 all squared is equal to 9. 4 times -3 is equal to -12 plus 4. And then once you add all of that up, you'll get 1. So therefore we can say f of -3 is equal to 1. Okay, and so that is how we do simple substitutions using functions, and essentially that's the best example for using function notation and what function notation is useful for. So then the next important thing, which tends to be most students' least favorite part about functions, is domain and range. Now, speaking from my experience, I didn't love domain and range, but once you sort of get used to it, it's not too tricky. So you may have been introduced to this in year 10, so you may remember that your domain is just the x values for which a function is defined. So on which x values are we going to have a matching y value? And then your range is kind of the opposite. It's the y values for which a function is defined. So essentially, where on the y-axis is there a matching x coordinate? So if we're looking at this example question here, find the domain and range of y equals x squared. First thing I can say to you is your domain and range questions are so much easier if you draw yourself a graph, because then you can actually literally see where things exist. Okay, so we've got this graph here for y equals x squared. It is a pretty basic graph. You probably can see it in your head as well. It's just the basic graph of your parabola. You haven't moved the vertex at all, so your vertex is here at 0, 0. So if we're thinking about the domain, we want to think about the fact that our parabola, unless we've put limits on it, will continually just go wider and wider and wider and wider and wider and wider along both sides of your x-axis. So essentially what we can say for the domain is that our domain is equal to all real x, or x from negative infinity to infinity. So the reason that we can say this is because our x's just get wider and wider and wider and wider. So for every single x value, there will be a coordinating y value, because we've not put any limits on how wide x can get. Then when we're looking at range, we want to see, with parabolas, we look where is our vertex, and our range is from the vertex up if you've got a concave up parabola. If your parabola is concave down, your range is from the vertex down. So here we've got our vertex at 0, 0, so then our range is going to be y greater than or equal to 0, or you may write that as 0 to infinity for your range for y. So the reason for that is because for every value of y greater than 0, there is going to be a corresponding value for x that gives a definite coordinate on our x-axis. Okay, so that's a pretty simple example of domain and range. So it will get a bit harder when you start doing more examples in class and things like that. But just as being your introduction to domain and range for today's little bit on functions, we'll just leave it at that. Just remembering that your domain is for what values of x are you going to have a matching y, and your range is for what values of y are you going to have a matching x. Okay. And yeah, if I can give you any tip for domain and range, draw the graph. It's so much easier when you can see what you're trying to find the domain and range of. So we'll have a little bit of a look at hyperbolas. So the next little bit of today's lecture is just going to be, I guess, a focus on some of your specific function types that you need to know of, and that you need to be able to sort of use and manipulate, doing a whole bunch of different things. But we're going to look at each of them together. So the first function we're going to start with is your hyperbola. Some schools and some textbooks will also refer to this as the graph of the reciprocal. So if you see it written like that, that just means hyperbola. And so a hyperbola is a discontinuous function in the form xy equals k or y equals k on x, where k is a constant value. So essentially what that means here is that if we have a discontinuous function, pretty much just means there's two segments of our function, and that there's going to be some values for x or y. With hyperbola it's talking about x, but discontinuous can also mean y, where the graph doesn't exist. Okay, so there's going to be some values for x where our graph cannot and will not exist. Now, these equations may look a little familiar, xy equals k or y equals k on x, if you remember doing inverse variation. So these do look like the equations for inverse variation as well. So yeah, discontinuous function means your function is not a continuous curve. There's at least two segments to it. Some graphs will have more. And so when we're looking at a hyperbola specifically, our graph is in the form of two discontinuous curves that have asymptotes in the x and the y-axis that they cannot cross. So an asymptote is essentially just a line which your curve will approach, but it will never touch. So looking at this graph of a hyperbola here, we can see that this is just the basic graph of y equals 1 on x. So that's like your basic hyperbola, kind of like how if you had a parabola, like your basic parabola is y equals x squared, your basic hyperbola is y equals 1 on x. And so essentially at that point, your asymptotes exist at x equals 0 and y equals 0. And your graph will never hit those 2 points if you just have the basic hyperbola. And then your asymptotes will change as you change your hyperbola. So as you move it up, down, left, right, dilations, or anything like that, you will change your asymptotes as you change your function. So looking at some more specifics of our hyperbolas, if your k is positive, then your curve is going to exist in the first and the third quadrant. So I'll show you guys this example graph here again. Remembering, whenever you do maths, your quadrants are labeled 1, 2, 3, and 4. Okay, starts in the top right, goes anti-clockwise. Okay, this will come back when we look at trig. When you do some stuff with trig, your quadrants in trig are also labeled as such, 1, 2, 3, and 4. So if our value for k is positive, so if we have a positive constant, then we are going to have a graph in the first and the third quadrant. If k is negative, then our graph is going to exist in the second and the fourth quadrant. Then when we're looking at our equation again, the larger our a is, that means the further away the curve will bend from your asymptotes when we're looking at the equation in this format, y equals k over x minus a plus b, where a and b are the transformations you can do to your graph, where it'll move it left and right, up and down. Okay, so similar to moving any other graph, if we have x minus a, this is moving our graph left and right, and then the plus b is moving it up or down, depending on the values for a and b. So the bigger a is, the further away the curve is bending from the asymptotes. Okay, when we have our graph in this format, our asymptotes, our x asymptote is equal to a, and our y asymptote is equal to b. Now, the reason for this is because we can never have our bottom of our denominator, bottom of our fraction, or also known as the denominator, can never equal 0. So x minus a can never equal 0, so therefore x can never equal a. The reason that b becomes the y asymptote is because our original asymptote occurs at y equals 0. So if we move it up or down, we're essentially just moving that original asymptote with us. Okay, so another example question for you guys to have a go at. I'll give you maybe a minute or so. Have a look at this question, see if you'll be able to graph y equals 5 over x minus 2 minus 3. And then we'll go through it in about a minute. If you need more time, you can just pause the video as well. So I'll just give you about a minute to have a go and look at this question. Alrighty, so looking at this example question, first thing we want to do is rearrange our function so that we can work out where our asymptotes are going to be at. So we can see that our asymptote here is going to be is going to be 2. So our a value here, and then our y asymptote is going to be at -3 because in our original function we've got our asymptote at -3. I'm sorry, our value for b at -3, which means the asymptote is then going to be at -3. So from there, what we want to do is find our intercepts. Now, hopefully by now, you've had a lot of experience finding intercepts. So we find our x-intercept when y equals 0, and our y-intercept when x equals 0. So that's going to give us these two coordinates as our x and y intercepts. So once we've found the asymptotes and the intercepts, we're ready to sketch our graph. Okay, so hopefully you guys have had a go sketching. So we end up here with this graph. So the first thing we do when we sketch is always plot in your asymptotes. Draw them as, or they're usually drawn as, and how I like to draw them is just as dotted lines. Make sure you use a ruler so that they're accurate, and we want to make sure that they are to scale. So first thing you want to do, draw in your asymptotes. Second, we want to be working out which quadrants is our graph going to exist in. So remembering that your quadrants are going to be relative to your asymptotes, okay? So if we're looking at these green lines here, this creates our new 4 quadrants. So we've got 1, 2, 3, and 4. Okay, so all of this, even though some of it is above the x-axis, some of it below, all of this makes up quadrant 1, all of this quadrant 2, quadrant 3, and quadrant 4. So going back to our original equation, we can see that we've got a positive value for k, so our graph exists in the first and the third quadrants. Then we just want to plot in our intercepts, so our x-intercept, our y-intercept, and then we just want to draw our lines for our hyperbolas going towards both of our 2 asymptotes. Just like that for hyperbolas. So hopefully that made sense. And yeah, we're going to have a go now looking at circles. So circles have a very distinct equation, and you'll be able to pick up the equation of a circle really easily. They exist in the form x squared plus y squared equals r squared, or alternatively as x minus a squared plus y minus b squared equals r squared. So this is your basic equation of a circle. If you've got x squared plus y squared equals r squared, and the center is 0, 0. And the radius is equal to r. So in general, the domain and range of this basic function, the domain is between r, x, and negative r, and the range is r, y, and negative r. Okay, so essentially the reason that is because your radius spans the widest point on your x-axis on both sides. You'll have r and negative r as the widest points, and then y and negative y as your shortest and tallest points. Then the equation of a circle with the center A, B, and radius r is given in this format. So you'll have x minus a squared plus y minus b squared equals r squared. Okay, so essentially when we're looking at this as a more complex equation for a circle that's had some movement to it, we can find the radius of, the center of our circle with A and B. Okay, it's important to notice here that minus A and minus B give you the coordinates A and B for your center. If you had x plus A and y plus B, you'd have the coordinates negative A and negative B. Okay, so the center is the opposites of what we've got going on here. And then again, the same thing. Your radius is the square root of whatever all of that's equal to. Okay, so next example question, I want you guys to have a go sketching this circle and stating its domain and range if you've got x minus 3 all squared plus y plus 1 all squared equals 4. So I'll give you guys probably about 1 minute to have a go at this, and then we'll look at the answers together. Again, just as a side note, as you guys are doing this, if you are watching live, feel free to ask any questions, because I'll be sitting in the chat to answer your questions as well as we're going on. And feel free to pop your answers in the chat as well. So if you can find the domain and range, pop it in the chat as we're going on as well. So I'll give you guys maybe 20 more seconds just to have a go at this. Alrighty, so let's have a look at this question together. So again, finding domain and range is so much easier when you have a picture in front of you, because you'll actually be able to see, specifically with circles, they do end. There's really distinct points. So a bit of a tip there, your domain and your range for your circles is never going to be to infinity, because your circle is a defined little thing. So this is what we end up with as our circle. So we have center here at 3 minus 1. And we can see that because that's the opposites of our A and our B, is 3 and minus 1. Then we've got 4 here. So that's r squared. So therefore r is equal to 2. So when you're drawing your circles, plot your center and then go 2 in each direction, and then just draw the curve around your circle. When you are drawing circles in your exams, your examiners are not looking for you to draw perfect circles. They acknowledge that it's hard to get the curve exactly right, but they want to see that you've got your center right. They want to see you've got these 4 distinct points, and then they just want to see sort of like a general, you've tried to draw a curve connecting them. They're not looking for exact perfect circles. So we've got here 5 and -1, and +1 as our domain. So we can see that from our graph. Otherwise, what we can do is think if our center coordinate for x is 3, we just +2 and -2 on either side, which gives us the domain of x is between 5 and 1. And then we can see from the graph that our range is from 1 to -3. Otherwise, our y coordinate is -1, so we can just +2 and -2 to work out our range here as well. Okay, and then that's all you really have to do, or when you have to graph a circle. So in some cases, you're going to be given the equation of a circle with x squared plus y squared plus ax plus by plus c equals 0. And you're going to be asked to solve this. Sometimes if whoever's written your paper is nice, they'll tell you that you have to solve it by completing the square. Otherwise, they'll just give you that equation and you're sort of just expected to know that you need to complete the square. So the way that you're going to recognize this is because it'll be in your exam as x squared plus y squared. There may or may not be ax and by, but there will always definitely be x squared and y squared. And that's how you'll recognize that you've got the expanded version of the equation of a circle, and you're going to need to complete the square in order to find it. So that equation, when you've got x squared plus y squared plus ax plus by plus c, is essentially just the expanded version of the equation of a circle with a few of your factors missing, which is essentially what you're trying to create with completing the square. So by completing the square, you find the missing factors so that you can then find the whole equation of the circle. Now, completing the square is something that you do look at in year 10, which is why I don't have an example of it just yet. So what I'm going to get you guys to do is have a go completing the square for A and for B. I'll give you probably about a minute or so. See if you can remember it. If you don't, we're going to go through it together anyway. So see what you remember about completing the square, and then we'll go through the example together. Okay, so I'll give you about 10 more seconds maybe. Again, if you need more time, just pause the video so you guys can complete it. Or if you've had enough of waiting and you're not sure how to do it, you can skip ahead and look at the solutions. So when we are completing the square, what we do, we've got x squared minus 8x. We half this, we half our coefficient of x and square it, okay? So half of negative 8 is negative 4. Negative 4 all squared is 16, okay? So we do the plus 16, then you've got y squared plus 10y. Half the coefficient of y equals 5, square that is 25. Now, what we've done on this side is we have moved our constant of 32 across, and then we've added the 25 and the 16 to this side as well, okay? Because essentially we can't just go adding like numbers into the equation. What we have to do is make it equal on both sides. So as long as we add 16 and 25 on both sides, our equation is still equal. So then we add the 25, we add the 16, and we end up with this equation here. Now, with the two examples that I've given you, I actually have given them to you in order. So I've got x squared minus 8x plus y squared plus 10y. Sometimes it'll come a bit muddled, so it might be like x squared plus 10y plus y squared minus 8x. First thing you want to do, arrange it so you've got your x's together, your y's together. Then half your coefficients and square them, making sure you add them to both sides. And then you'll get something looking like this. Now, from there, what you can do is go x minus 4. So in this case, x and whatever you halved. So the half of the minus 8 gives us minus 4, and we square that, okay? All in brackets. Same thing with the y's. You do your y plus whatever we halved, which was plus 5, all squared, and then that 9 comes from just doing that maths there. And then you can see here that you have the equation of a circle. So we can say our center is going to be at 4, negative 5, because we're just taking the opposites. And our radius is 3, because 9 is representative of r squared. So you get our radius of 3. Okay, so then looking at the second equation, if we had x squared minus 2x plus y squared plus 24y plus 120, again, recognizing that this has sort of been sorted out for you, all your x's are already together, the y's are already together. So what we want to do is we've got x squared minus 2x, half of 2x is minus 1 squared, we just plus 1. Then same thing with the y's, we've got y squared plus 24y, half of 24 is 12 all squared is 144, so we add the 144 to this side as well. From there, we can start creating our sets of brackets. So we open our first set of brackets with x, just our pronumeral, whatever we halved, all squared, then y plus whatever we squared, which is 12, all squared, and then we do this math for negative 120 plus 144 plus 1, we'll get 25. From there, we use our opposites to find the center of our circle. So here we're going to have a center of 1, negative 12, and our radius is going to be 5 because 25 represents r squared, so therefore our r is equal to 5. And that's pretty much all you need to know how to do with your circle. So then this is looking at semicircles. So the equation of a semicircle that's above the x-axis with center 0, 0 and radius r is going to be equal to y equals the square root of r squared minus x squared. So that will have domain negative r and r and range between r and 0. So that's when we have the center 0, 0 as well, so keep that in mind. And then when we have the equation of a semicircle that occurs below the x-axis, again with the center 0, 0 and the radius r, we're just going to put a negative in front of that square root sign, and that means it's going to be below the x-axis as well. So it's going to be the half of the circle that occurs below the x-axis, that's going to be concave up. So yeah, that's pretty much all we really need to know about semicircles for now. They're a little bit confusing when you start to move them around a little bit, so we won't go into that today, and I'll leave that for you guys to go into in class when you do functions. But just sort of knowing that in general this is what the equations of semicircles looks like is going to be enough for you guys for now. So next we're just going to have a bit of a look at absolute values. So you may know absolute values, but you might not know what the graph of an absolute value looks like. But essentially the absolute value is just the positive distance away from 0, denoted by these sort of straight lines with x or whatever number in the middle. Essentially, you're just removing the negatives if they're there. Yeah, so it's pretty much just the distance away from 0 that something is, disregarding the fact that it's moving in the positive or the negative direction. It's just like the absolute positive distance away from 0. So I'll quickly go through these. So essentially the absolute value of negative 3 is just 3, because essentially we're just removing the negative. The absolute value of 3 is just 3. Absolute value of negative 11 is 11. Absolute value of 11 is also 11. Then we have an equation here using some absolute values to solve. So 5 minus the absolute value of 2 minus 3. So this is equal to negative 1. So then the absolute value is going to be 1. So we've got 5 minus 1, so that's 4. And then we've got 4 plus the absolute value of 5 minus 8. So 5 minus 8 is going to be equal to negative 3. The absolute value of that is just going to be equal to 3. So then 4 plus 3 equals 7, minus the absolute value of 5. So 7 minus 5 is going to give us 2. And that's pretty much how you use the absolute value. And then there's also a graph that helps us denote the absolute value. So we know that absolute values make things positive. So therefore, when we're given a graph that's an absolute value, every single y value is going to be positive. So essentially what you're doing is just making all of your y values positive, and your graph ends up looking like a V. So when you're sketching your absolute value graphs, all you really need to do is sketch one side of them, and then they're symmetrical, so you just draw the exact same thing on the other side. And all your absolute value graphs are going to look like a V. Okay, you move this graph around the same way you'd move like a parabola or a straight line. You know, you can do the plus or minus to move left and right, up and down as well. Okay, changing the gradient makes it steeper or wider as well, just like it would for a regular graph of a straight line. Alrighty, and the last little bit of functions we're going to look at for today is looking at even and odd functions. So even functions are functions that are going to be symmetrical about the y-axis. Or in other words, they're going to have a line of symmetry about the y-axis. So this is seen in things like semicircles and parabolas, in that they are exactly symmetrical on either side of your y-axis. So this can also be true for parabolas that you move around. So they're not always going to be symmetrical about the y-axis, but if you move your parabola to the left or to the right, it's just going to be symmetrical about the middle point at the vertex. Okay, and so the reason that we can prove this, or how we prove this, is if you can prove that f of x is equal to f of negative x, you're going to have an even function. Okay, so the easiest way to think about this is thinking about it in terms of y equals x squared. So our normal fx is equal to x squared. And then if we have f of negative x, we're going to have negative x all squared. And we know that if we do a negative squared, we just end up with it's positive. So it's also going to be equal to x squared. Okay, then their opposite is the odd function. And so odd functions are functions that have a point of symmetry about the origin. So essentially what that means is if your graph is rotated 180 degrees about the origin, it's going to give the original graph as well. So this is seen in cubics and hyperbolas. And so essentially what that means is if we rotate this graph 180 degrees around, if I line it up properly, we're going to have the exact same graph. Okay, let's rotate it 180 degrees, exact same graph. Okay, 180 degrees, the exact same graph. Okay, so essentially that's what we mean when we're looking at odd functions. Okay, so you can prove something is an odd function if f of x is equal to negative f of negative x. Okay, so essentially if we look at this graph here, we have y equals x cubed as our fx. And then if we had negative f of negative x, you'd have negative of the negative x cubed, which you'd end up with negative times the negative, which would get you back to just x cubed. Okay, so we've got some example questions to look over. So I'll give you guys maybe a minute or two to have a go at these questions to prove that some of these are even, odd, or neither. So it is possible that your graph is not going to be even and it's not going to be odd. So yeah, I'll let you guys have a go at these. I'll give you about 2 minutes. Type your answers in the chat if you're watching it live. If you want more time, pause it. If you don't want any time, skip ahead to the solutions. Okay, so we'll go through the solutions for part A first. So prove that fx equals x squared minus 4 is an even function. So we know that something is going to be an even function if f of x equals f of negative x. So we need to find what is f of negative x, and we do that by substituting in negative x wherever there was an x in our original equation. So then here we're going to end up with negative x all squared minus 4. Once we do this square, we know that if we square a negative, we just end up with the positive. So we're going to get x squared minus 4, which is equal to our original f(x). So therefore we can say f of x is an even function. And it's as simple as that to prove that something is even. To prove that something is an odd function, if we've got f(x) equals negative f of negative x. Okay, so for our original function here, x cubed for part B, if we want to find negative f of negative x, we want to do negative of negative x cubed, which we then end up with two negatives that when we multiply them together will cancel each other out to get just x cubed, which is equal to f of x. So therefore, our fx equals x cubed is going to be an odd function because fx equals negative f of negative x. Okay, and that's all we have to do for that one. So then for part C, prove that fx equals 3x plus 5 is not even nor odd. We first need to disprove that it's not even. Okay, so whenever you get a question that says prove this is not even and prove it's not odd, separate it into two sections. First prove it's not even, then prove it's not odd. Okay, so for something to be an even function, f of x has to be equal to f of negative x. So in this case, f of negative x, if we substitute that in, we'll get 3 negative x plus 5, which leaves us with negative 3x plus 5, and that does not equal f of x. So therefore, we can say that our fx is not an even function. Then for proving it's not an odd function, an odd function occurs if f of x equals negative f negative x. So in this case, to find negative f of negative x, first substitute in negative x to where there's x, and then we need to make all of that entire function negative. So then we end up with, when we multiply this out, negative 3x plus 5, all of that is negative. So then we multiply that negative out, you'll get 3x minus 5, which does not equal our f of x. So therefore, fx is not an odd function, and we can therefore say that we do not have an even nor an odd function when we are looking at 3x plus 5. Okay, and that's all you need to do with functions in proving that they're even and odd. It can be a little bit tricky to get your head around the f of x and the f of negative x and the negative f of negative x. So I would just recommend doing lots of practice with it, but that's the only two rules that you need to know to be able to prove whether something is even or odd. Alrighty, so that brings us to the end of our overview of functions today. So we're going to do, I guess, a bit of a break from maths, more looking at some study tips for the next few minutes. So if you guys do have like general questions about study tips as well, feel free to ask them in the chat if you're watching this live. Alrighty, so the first study tip, I guess, is about asking lots of questions. So this is not so much a study tip, more something that you have to be actively trying to do in class. But if you don't understand something in class, the chance is you're probably not going to understand it when you try and do your homework later either. So make sure that you ask as much questions, or as many questions I should say, as you need to in class to make sure you have a really good grasp on a topic, because there's no point practicing a topic, doing homework and past questions and things like that if you don't understand it to begin with. Okay? Second study tip, find questions from a range of sources. So past HSC papers, about 20% of your HSC paper comes from Year 11 content. So if you flick through some of these past papers, you will see questions that are actually based on the Year 11 content. Same thing with trial papers, ATAR notes, topic tests. Honestly, if you just Google like Year 11 Maths Advanced, trigonometry test or like end of year exam or something, you should have a fair few things that pop up. So find as many questions as you can, because I think if you only practice questions from your textbook, you're not going to get a wide variety of questions, and you're not going to be able to answer a lot of exam style questions, because most textbooks are aimed at helping you solidify your understanding rather than helping you prepare for an exam. So make sure you are seeking out a wide range of questions so you're ready for anything they'll throw at you in your exam. Thirdly, be consistent. I think doing your maths homework every day if you get it, or setting a routine for every 2 days or whatever, doing summaries for maths at the end of every week, things like that, constantly going, if your school has like a maths study help or something, go to that every week. Just be consistent with what you do, because the more consistent you are, the easier it is for your brain to understand what you're doing. I think creating good habits will also just help you to understand the content better, because your brain is going to be in the zone, ready to focus on that as well. And then finally, make your own formula sheets. So as you go along, write down, whether that's like literally on like a Word doc or your computer, in the back of your maths book or something, write down the formulas that you learn and explain what they are, when you use them, and put in a key example into that formula sheet. So that way, at the end of the year, at the end of the topic, when you can't remember what a specific formula is, you can't remember how to use it, you already have a complete summary of every formula that you need and example questions, so that you know exactly how you're meant to use it as well. I did that a lot in Year 12. I would say mine was more of a formula book than a formula sheet. I just had like a little A5 book that, as I went through the year, in Year 11 and 12, I wrote down all of the formulas I needed, when to use them, and key examples. And I'd say it's one of the biggest reasons that I did so well in maths in Year 12, because I just knew, and I had something to go back onto when I forgot something or forgot how to use a specific formula. And then the most important study tip is practice, 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 practice. Maths is not a subject that reading of your notes is not going to do anything for you unless you are accompanying that with practice questions. Maths is all about calculations, it's all about doing, and the only way to get better at doing is to practice. So make sure you just seek out as many questions as you can, do them as often as you can. I mean, like, don't try and do them every day because you're going to burn out and you're going to hate maths. But set yourself a schedule that maybe, 3 or 4 days a week you're going to be doing maths practice or something like that. Okay, so just practice, 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 practice is my biggest study tip I can give you for maths. So we're going to move on to the third part of today's lecture, looking at trig. So some basic revision, some stuff you would have looked at. SOHCAHTOA. Basic revision of what each of these is. So your sine theta is equal to the opposite over the hypotenuse. Cos theta is equal to the adjacent over the hypotenuse. Tan theta equals the opposite of the adjacent. Easy to remember. I'm pretty sure they actually are in your formula sheet as well, even if you don't remember them. But yeah, just some basic revision of the basis of trigonometry. It may seem super simple, but it does come up a lot, and you really do need to know your SOHCAHTOA. So please keep that in mind whenever you're doing some of your trig stuff. You actually will get a lot of questions specifically as you learn to do some of the harder stuff in trig. You're going to forget that SOHCAHTOA exists, and you'll get like questions on right angle trigonometry, and you're going to forget that you can just use SOHCAHTOA to do it. Okay, so SOHCAHTOA does not become redundant once you learn to do non-right angle trig. So yeah, remember your SOHCAHTOA stuff. This is it. Just a bit of a practice question. If tan x is equal to 4 and 3, find cos x and sin x. So I'll give you guys just a minute to have a go at this one. Pause, skip ahead, do whatever you need to do to be able to do this question. Alrighty, so let's have a look at this one together. So a lot of this trig section of the lecture is going to be just about doing example questions. So hope you've got some paper in front of you. So if we've got tan x equals 4 on 3, this essentially represents the opposite over the adjacent. So we know our opposite is going to be 4 and our adjacent is going to be 3. So therefore, using Pythagoras' rule, in order to find the hypotenuse, we're going to have the square root of 4 squared plus 3 squared. So 4 squared is equal to 16, 3 squared is equal to 9. If you add those together, you're going to get 25. Square root them, you're going to get 5. So we can therefore say here our hypotenuse is going to be equal to 5. Therefore, cos x is going to be the adjacent, which is 3, over the hypotenuse, which is 5. And sine x is going to be the opposite, 4, over the hypotenuse of 5. So you're going to get 3 on 5 and 4 on 5 as the solutions to cos x and sine x, respectively. It's actually a pretty common exam style question that you may get asked a bit. So make sure you're familiar with how to do this sort of thing, and make sure you're familiar with how to do it if I put, negative 4 and 3 here or something like that. Alrighty, so the next thing we're going to look at, which you've probably been introduced to already, is the exact ratio triangles. So these are actually also in your formula sheet. This little snippet here is directly from that formula sheet. So essentially these exact ratio triangles are little triangles that allow us to find exact values when we're answering trigonometric questions. So you'll find that when you're doing this topic, specifically in year 11, a lot of your questions are going to begin with, using the exact value or, find the exact value of. And essentially what they're getting at is they want you to use these ratios to find exact values. Now, the reason that they're called exact is because a lot of them use surds. So essentially they're asking for the non-decimal form of the surd. So I'm assuming you guys have been through how to find these ratios in class. If not, it's just using your basic SOHCAHTOA. For example, if we're trying to find the sine of 60 degrees, we're going to have the opposite, which is root 3, over the adjacent, which is root 2, and we get the sine of 60 degrees is equal to root 3 on 2 as the exact value. So you don't have to actually remember these ratios because they are in your formula sheet. Like I said, these exact triangles are there. But you also just have to know how to use them and what they mean when a question says find the exact value. Now, something I will say here is that just because a question does not say find the exact value does not mean you shouldn't. So if you end up with a question, you do some working and let's say you end up with, this line of 60, what does it equal? Do put the exact value in there as well, because they won't always specify that's what they want you to do. They're just going to assume that you know, unfortunately. So yeah, just because something doesn't say exact value doesn't mean you won't have to. So just keep an eye out whenever you're doing your trig questions about whether or not you have any of your sine, cos, and tan, 30, 45, and 60 degrees, whether they come up at all. All right, so the first big thing of non-right angled trig is the sine rule. So your sine rule essentially allows us to find unknown lengths and unknown angles in right angled triangles. And we use the sine rule if we are given one side and two angles and we want to find a side, or if we want to find an angle if we've been given two sides and one angle. Okay, so essentially the sine rule looks at this triangle, big A, big B, big C, and then we've got little a, little b, little c, and it's essentially relying on the fact that ratios exist in any non-right angled triangle. The length of A over the sine of big A is equal to the length of little b over the sine of big B, which is equal to the length of C over the sine of big C. And those ratios exist and hold true for any non-right angled triangle. So like I said, we want to use this when we've been given either two angles and a side or two sides and an angle. So we're going to look at some practice questions because I think the best way to work out and understand this rule is to look at practice questions. So this one comes from the HSC from 2006. It was worth 2 marks, and it says, find the value of theta in the diagram, give your answer to the nearest degree. So the reason that we know that we have to use the sine rule here is because we want to find an angle and we've been given two sides and an angle. Okay, so if we want to find something and we've been given one more of that thing, so we've been given one more angle, and 2 more sides, then that's how we know we're going to be wanting to use the sine rule. So I'll give you guys a minute just to work out and see if you can play around with this a little bit to see if you can calculate what theta is equal to, correct to the nearest degree. So I'll give you guys just a minute. Again, you can skip ahead or pause if you're going to need more or less time. Okay, so when we're thinking about the solution here, we need to use our ratio that the length of A over sine A is equal to the length of B over sine B. Okay, so in this case, let's look at our diagram again. This angle is going to be sine A, and then our corresponding opposite, so direct opposite. Another way to think about this is the length of the side from which the angle does not touch, right? So you see this angle is formed by the length of this side and the length of this side, but the length that we care about is the one that it does not touch, okay? So if this is sine A, then 5 is going to be our little a. If we have sine of 33, then 9 is going to be our little b. Okay, so we'll end up with A equals 5, sine A equals sine theta, B equals 9, and then sine B is equal to sine of 33. Then we just substitute those into our ratios, so we'll end up with 5 over sine theta equals 9 over sine 33. Once we get rid of or move that 5 across to the other side, we're going to get sine theta is equal to 5 sine 33 over 9, which will equal the inverse of sine of the 5 sine 33 of 9, so we can get that theta by itself. Then if you pop that in your calculator, making sure that your calculator is in degrees, something that goes wrong very frequently in your 11 and 12 trig is doing things in radians when you should do them in degrees, and doing things in degrees when you should be doing them in radians. But this question has asked us to find to the nearest degree, so we know we are in degrees, not radians. So if you pop this into your calculator, making sure it's in degrees, you'll end up with 17.61, rounded off to the nearest degrees is equal to 18 degrees. So it's pretty simple, just making sure you get these ratios right, okay? So if you're putting the side in the numerator, you've got to make sure you're putting the side in the numerator on both sides, and your angles in the denominator on both sides. It actually doesn't matter if you put the sine in the angles in the numerator, so long as you do it on both sides. So this could also be written as sine A over A equals sine B over B, and you will still end up with the same answer. So long as you're doing it to both sides, the ratio will remain the same. All right, looking at a second question using the sine rule. This is from the 2002 HSC. So in the diagram, XYZ is a triangle where Z, Y, X is 45 degrees and Z, X, Y is equal to 60 degrees. Find the exact value for the ratio X over Y. This is a little bit trickier and it's worth 3 marks. So I'll give you guys a minute to have a look at this. Again, feel free to skip ahead or pause the video. And if you're watching live, feel free to pop your answer in the chat as well to get some feedback, or ask any questions in the chat if you've got them as well. Alrighty, so hopefully you guys are having a go at this. I'll give you guys maybe 30 or 40 more seconds. Again, feel free to pause it if you do need more time. So these questions are super common in the HSC as well. So not just year 11, but you do need to know how to do these in your HSC as well. Okay, so we're gonna have a look at the answers. So if you're not ready for the answer, pause the video here. Otherwise, we're using our ratio again. So this time we're just gonna do x's and y's instead of a's and b's. Doesn't really matter. So we're going to have little x over the sine of big X equals little y over the sine of big Y. So we're thinking about this. Sine of big X equals sine 60, right? Because if we're looking at our example here, the sine of our big X is sine 60. Then sine of the big Y is equal to sine of 45. Okay, so it's just that one over there. Then when we're thinking about our exact ratios, okay, anytime you see 60, 40, or 30 attached to sine, cos, or tan, we're thinking about our exact values, our exact ratios. Okay, so sine of 60 is equal to root 3 on 2. Sine of 45 is equal to 1 on root 2. These are on your formula sheet in those little triangles, so you don't have to stress about remembering them. Although I will say with enough practice, you do sort of start to just remember what they are. Then from here, what we want to do is we've got x over root 3 on 2 is equal to y over 1 on root 2. Because what we're doing is if we know that sine 60 is equal to root 3 on 2, we're substituting that into our equation. So we've still got little x on top, and we know what sine x is equal to. So we've got little x over what we know sine x is equal to. Okay, same thing on the other side, little y still on top. We know that sine of y is equal to 1 on root 2, so we're putting that in the denominator. So therefore, we can say that x on y is equal to root 3 on 2 multiplied by root 2 over 1. And then we just end up with x on y is equal to root 6 on 2. Okay, so this question isn't too tricky once you remember that you do have your exact values that you can rely on for any question to do with 60, 45, or 30 degrees and either sine, cos, or tan. Okay, so just remembering that those ratios exist is so super important. As you can see, because this question would be pretty much impossible to do if you didn't remember what those ratios were. Okay, so that's it for the sine rule for today. Next is the cosine rule. So, just like your sine rule, the cosine rule allows us to discover properties of non-right angled triangles, and it uses the same sort of triangle with your angles being represented by your capital letters, sides being represented by lowercase letters. So, our cosine rule is equal to a squared equals b squared plus c squared minus 2 times b times c times cos a. I've written that a bit of a weird way because on your formula sheet it's given to you as c squared equals a squared plus b squared minus 2 times a times b times cos c. I mean, it's the exact same thing, just using different letters. So we've got a squared equals b squared plus c squared minus 2 times b times c times the cos of a. The big thing to remember here is that you just have to make sure that if you're doing a squared here, so this side, you do the corresponding angle, so the opposite angle to this side. So we're using the cosine rule when we need to find the third side if we've already been given two sides and an angle, or if we've been given all three of the sides and we need to find an angle. So just like the sine rule, I think this is easiest to understand when we look at some practice questions. So this is from the HSC question as well. I think this was worth maybe 2 or 3 marks. So in the diagram, AC which is this one here, is parallel to DB, which is represented by these little arrows. AB is 6 centimeters, BC is 3 centimeters, and AC is 7 centimeters. Use the cosine rule to find the angle ACB correct to the nearest degree. Okay, so this one, it's been nice to us. It's told us that we need to use the cosine rule. But even if it didn't tell us that, and it asked us to find the size of angle ACB, we would know that we have to use the cosine rule because we've been given all 3 sides and we've been asked to find one angle. Okay, so if you've been given all 3 sides and the question asks you to find an angle, should be alarm bells going off that we're using the cosine rule. So I'll give you guys a minute just to have a go at this one, and then we'll go through the answer together. Alrighty, so first thing we want to do is we want to rearrange our equation so that we can get the cos of C by itself, okay? So we want to get this bit by itself. So we just rearrange our equation, which I think they actually give to you on your formula sheet if I'm not mistaken. Otherwise, just rearrange it like you would any other algebraic equation, and you would get cos C is equal to A squared plus B squared minus C squared all over 2AB, okay? We need to get this cos C by itself because we're trying to find this angle C. So then we've got cos C equals 3 squared plus 7 squared minus 6 squared, making sure that whichever side you're subtracting is the one opposite the angle you're trying to find, okay? So we're trying to find this angle, so the side we are subtracting has to be the one opposite to that. Okay, so then we get 3 squared plus 7 squared minus 6 squared over 2 times 3 times 7. So we'll get cos C is equal to 22 over 42. Then we just take this cos across by making an inverse, and we'll get that angle C is equal to cos to the negative 1 of 22 and 42, which if we put that in our calculator, making sure it's in degrees, we'll get 58.41. Rounding off to the nearest degrees, we get 58 degrees. Okay, so again, this is just another rule that you pretty much just have to substitute things into an equation, so not too tricky. And then we're going to do this practice question as well, which is from the 2001 HSC, and it's worth 4 marks, which is like fairly hefty for a HSC question, because if you think about it, like 4 marks is like 1/25 of the paper. So you don't go around giving 4-mark questions out too often. Okay, so the diagram shows a triangle with sides 7, 13, x centimeters, and an angle of 60 degrees is marked. Use the cosine rule to show that x squared minus 7x equals 120, and hence find the exact value of x. Okay, so again, it's been quite nice to us. It's told you that you need to use the cosine rule. Otherwise, if it didn't tell you that, you would know you need to find the cosine rule because it's given you 2 sides, an angle, and it's asked you to find the 3rd side. Okay, so I'll give you guys maybe a minute and a bit just to have a go at this question because it is a bit tricky. And I just want you to think about it before we go through it as well. So again, if you want to go straight to the answer, skip ahead, otherwise pause it and have a go. Or I'll give you about a minute, so see how much of it you can get done before we go through it together. Right, so we might have a look at this question. So with this, our cos rule, a squared equals b squared plus c squared minus 2 times b times c times the cos of a. First thing we want to do is just substitute in everything that we know. Okay, so we've got 13 squared equals 7 squared plus x squared minus 2 times 7 times x times the cos of 60. First thing to recognize here is that x is not the side associated with your angle. I think a lot of people tend to innately think that when you're being asked to use the cosine rule, that whatever side is marked with the pronumeral is the one that is going to be using the angle. But in this case, we've got to recognize that this angle is opposite from the 13. Okay, so in this case, our C is actually going to be 13 because C is whichever side is opposite your angle. Hence, we've got 13 squared equals 7 squared plus x squared minus 2 times 7 times x times cos 60. Now, I did just say C because I'm really used to thinking of it as C, but in this case, with the way I've written it, it is A. Anyway, so then we get 169 equals 49 plus x squared minus 14x times a half. A cos 60 equals, as cos 60 equals a half, which is why we get this half here. Because again, we're remembering that our cos 60 is an exact value, which we know is equal to a half. Okay, so then you get 2 times 7 times the x gives you the 14x times the half. So then once you've done that, if you subtract that 149 across, and then multiply the 14x by the half, you'll get x squared minus 7x equals 120, which is the first thing that they've asked you to find. Then in order to find x, we've got a quadratic. So move that 120 across, you'll get x squared minus 7x minus 120. Factorize that out, you'll get x minus 15 times x plus 8 equals 0. Therefore, x is equal to 15 and negative 8. Now, this is super important because usually in the HSC, marks are actually associated with discounting the solution. So you therefore say, however, because the length can't be negative, x is only going to be equal to 15. So it's super important that if you're going to discount that one, you know you have to discount the solution. And two, if you're going to discount it, that you give a reason as to why you have discounted it. Okay, so our length can't be negative, so therefore we can't have negative 8 as a solution. And so yeah, that's about it for cosine rule. It's again like the sine rule. The sine rule and the cosine rule and the area of a triangle, which we're about to look at, are all pretty much just about substituting things into a formula. So they're not too tricky, so they're good questions to get in your exam. So then area of your triangle allows you to find the area of a non-right angled triangle. Again, on the basis of this same triangle where your capitals are your capitals are angles, your lowercases are the lengths of sides. So your area, so this A is not equal to this A. This A stands for, let me see if I can write it, area. So area equals a half times A times B times the sine of C. So it's pretty easy. So we'll just have a look at a quick example question from the 2002 HSC. So I'll give you just a minute to have a look at this one. So in the diagram, LMN is a triangle where LM equals 5.2 meters, LN equals 8.9 meters, and angle MLN is 110. And so for 2 marks, calculate the area of the triangle LMN. The reason you know you have to use the area of a triangle formula is because it's literally told you to find the area and it's not right angled. So you need to use the formula for non-right angled triangles. Okay, so I'll give you just like a minute to have a quick go at this one. Alrighty, so again, this is not too tricky. Area of a triangle is just about substituting things into a formula. So our area equals half times a times b times sine c. So therefore the area of LMN is equal to a half times m times n times sine L. Recognizing here that you've got the two sides, and whichever side you're not multiplying, that's the angle that you use. So then area is equal to a half times 5.2 times 8.9 times sine of 110. So your area is going to be equal to 21.7 meters squared. Okay, and that's all you've got to do for that. So just, a little FYI. A lot of your trig is just about remembering rules and knowing how to apply them. So sorry about the spam that's happened and that we're about to go through, because it is pretty much just about remembering rules and knowing when and where to substitute things in. So we've been over sine, cos, and tan. Just another thing to sort of note, tan can also be expressed as sine over cos. And the reason that this is important is because it comes into play when we are looking at our reciprocal trig functions. Okay, so we've got cosec theta equals 1 over sine theta, so that's the hypotenuse of the opposite. Sec theta is 1 on cos theta, so the hypotenuse of the adjacent. And cot theta is equal to 1 on tan theta, which is equal to the opposite of the adjacent, which can also be written as the reciprocal of the tan we just looked at. So cot theta can also be written as cos theta over sine theta. So these are all your reciprocal trig functions. So pretty much you find them by just, flipping your normal trigonometric functions around. They are actually also written on your formula sheet, I'm pretty sure, so you don't even really have to remember them. So just knowing that they exist, that they're there, and when you see them in questions, recognizing that cosec is the reciprocal of sine, sec is the reciprocal of cos, and cot is the reciprocal of tan. It's pretty much all you need to be able to remember. And then from there, if you know that cosec is the reciprocal of sine, you know it's going to be hypotenuse over the opposite, and then the same for each of the following ones. Something else to know with trig is about trig identities. So looking at how to prove cos squared theta equals sine squared theta equals 1 is actually one of your syllabus points. I'm going to say it's going to be pretty unlikely that you're going to be asked to actually prove this. I've never personally seen it in a question, but it is in the syllabus, so you do need to know it. And then from that equation, you can then derive the second of the trig identities, that 1 plus tan squared equals sec squared theta, and 1 plus cot squared theta equals cosec squared theta. Now, this identity here is on your formula sheet. These two are not, so you do have to know them. And they are super, super, super important to know for when you get questions about trig identities. So we'll have a look at some of those example questions in a little bit, but just knowing that they're there for now is enough. So to prove it, our sine theta is equal to the opposite of the hypotenuse. So if we rearrange that, we can say our opposite side is equal to the hypotenuse times sine theta. Then if we've got cos theta, we're going to have the adjacent over the hypotenuse. So we can therefore say that the adjacent is equal to h cos theta, so the hypotenuse times cos theta. If we then use Pythagoras to do a squared plus o squared, so adjacent squared plus opposite squared equals hypotenuse squared, we'll get h cos theta squared plus h sine theta squared equals h squared theta, which you end up with h squared times cos squared theta plus h squared times sine squared theta equals h squared. Divide all of those things by h squared, and you end up with your cos squared theta plus sine squared theta equals 1. So like I said, I think it's unlikely that you'd actually ever get asked to do this, but it's not too tricky of a proof to understand. So it is worthwhile knowing, and I think it also does help you just with a general understanding of what's going on. So let's have a look at some practice questions. So I think trig identities questions are probably for me was the hardest part of year 11, both trig and maths in general. So let's have a look at this question, which says sec squared x plus sec x tan x equals 1 plus sine x on cos squared x. So we're being asked to prove this question. So how can we prove that the left-hand side is equal to the right-hand side. So you guys may not have seen trig identities questions before, so I'm just going to go through this first one with you. So essentially, in order to do this, all you need to do is prove that the left-hand side is equal to the right-hand side of your equation by just manipulating things in between. So the left-hand side is equal to sec squared x plus sec x tan x. And so that's like literally what the left-hand side is equal to. We haven't changed anything there. So then sec squared x is the same thing as writing 1 on cos squared x, because that sec squared x is just the reciprocal of the cos. Then we can write sec x as 1 on cos x and then multiplied by tan x. So this dot represents a multiplication. And then tan x is just sin x on cos x. So then once we do all of that, when we multiply these together, we would get sin x over cos squared x. So if we've got 1 on cos squared x plus sin x on cos squared x, add those two fractions together, we get 1 plus sin x all over cos squared x, which is equal to the right-hand side. And so that's all we need to do to prove that equation. So let's you guys have a go at these ones. So let's maybe give you guys a minute or so, have a go at part A, and then part B is tricky, so we might do part B together. So if you guys have a go at proving that sec squared theta minus tan squared theta equals cosec squared theta minus cot squared theta. Honestly, these are really hard, but they just rely on the fact that you know about your trig identities and what your reciprocal trig values are equal to and things like that. So have a go, remembering that you've just learnt this stuff, so if you can't do it or you're a bit confused, don't worry about that. Because honestly, you've just learnt it and you have so much time to perfect it. Okay, so let's have a look at these ones. If we've got sec squared theta minus tan squared theta equals cosec squared theta minus cot squared theta, let's first look at our left-hand side, and we've got sec squared theta minus tan squared theta. And then if we use the identity that 1 plus tan squared theta is equal to sec squared theta, so we just substitute 1 plus tan squared theta here, we'll end up with the fact that the left-hand side is equal to 1. Okay, from there, let's look at the right-hand side. So if we've got cosec squared theta minus cot squared theta, let's use the identity 1 plus cosec squared theta equals cot squared theta. Just pop this into our equation here, and we'll get the right-hand side also equal to 1. So therefore, left-hand side is equal to right-hand side, and we've just proved that identity there. So that's why it's really important that you know these identities, because they're not on your formula sheet. They are unfortunately just something that you do have to memorize. And so I'll go through part B as well. So if we've got 1 plus cot theta over cosec theta minus cos theta equals sec theta over tan theta plus cot theta, let's start by looking at the left-hand side. So we've got 1 plus cot theta over cosec theta minus cos theta. Then let's think about the fact that cot can also be written as cos theta over sin theta. Substitute that in and we'll get 1 plus cos theta over sin theta. Then think about cosec can also be written as 1 over sin theta, and then we don't change that cos theta. If you're ever stuck on these questions and you do have reciprocal trig values, just try putting in their sine, cos and tan values, and you'll usually get a bit of an indicator as to where you need to go. Then once we expand all of that, we'll get 1 plus cos theta over sine theta times sine theta minus cos theta. Multiply these brackets by the sine theta and we'll end up with sine theta plus cos theta minus cos theta equals sine theta. Okay, so the left-hand side is equal to sine theta. Then our right-hand side, we've got sec theta over tan theta plus cot theta. So we can also write sec as 1 on cos theta. We can also write tan as sine theta on cos theta. We can also write cot as cos theta on sine theta. Then moving these and making this denominator just into one fraction, we'll get sine squared theta plus cos squared theta over sine theta cos theta. Then we'll get 1 on cos theta multiplied by sine theta on cos theta on 1. Essentially because in order to get rid of this fraction in the denominator, what we do is we flip it and we multiply it by the numerator. And then we get 1 here because sine squared theta plus cos squared theta equals 1 because we know that we just proved that identity. So that was the identity that we proved just here. So we'll end up with 1 on cos theta times sine theta cos theta on 1 equals sine theta. So therefore the right-hand side equals sine theta and the left-hand side is equal to the right-hand side. And then that is all we need to do for that. Now that last trig proof was actually really hard. So if you're a little bit confused by it all, don't stress because it was really hard. And you have a lot of time to learn these as well. So what I'd recommend is that after you do trig identities in class or when you feel a little bit more confident with them, come back to this lecture, come back to the slides, have a go proving those identities again, and you'll have to see like how much you've grown as well in maths so far. So that's actually it for trig for today. So the last little bit of this lecture is just looking at exam techniques. So number 1, use the reading time to your advantage. My biggest tip, if you can take anything away from this, don't do the multiple choice in the reading time. If you do them in the reading time, 1, you're not going to be using the reading time the best of you that you can. The best way to use your reading time is to flick through the questions and to start to mentally mark the ones that you know you're going to have to allocate more time to. So then you've got a really good time management plan before the exam starts. Secondly, you're going to overthink them if you do them in the multiple choice because you're just going to spend a little bit too long thinking about them. Second thing is thinking about mark maximization. So realistically, it's unlikely that you're going to know how to answer every question. That's just a realistic view on sitting exams. So it's important to make sure that you don't get freaked out if you don't know how to answer a question, okay? Because every single person is going to look at that exam and have a question that they didn't know how to answer. But you should never leave it blank because leaving it blank means you have 0 chance of getting any marks. Trying to write down something, writing down, the equation that you think you might have to use or the formula or attempting to use that formula gives you a higher chance of getting marks, right? So leaving it blank, 0 chance of getting marks. Actually writing something gives you a good chance of actually getting marks in the exam. Thirdly, have faith in yourself. If you've studied hard, you're going to do fine in the exam, okay? You know more than you think you do, and I think a lot of time people get really nervous before exams, but once you get in there and you get rid of those nerves once the paper starts and you can actually read the questions, you will be fine. And that leads me to the 4th tip, which is just breathe, be calm. You won't do well in an exam if you're high stress. So just take a breath and remember that you do know how to do this and you've studied hard. But at the same time, enjoy year 11. Don't spend too much time studying, that you forget to have fun and enjoy the good parts of year 11 as well, because it is fun and you're in your last 2 years of school, so enjoy it. But that brings us to the end of today's exam. If you're watching live and you have any final questions, please type them in the chat. Otherwise, thank you for joining me today. I hope it was useful and I hope to see you in some lectures in the future. Bye everyone and best of luck with all your studies.